so it's 0 dB.
Yeah,
Do that?
okay, fine.
Thanks. Well, welcome to the Open University campus here at Walton Hall. We're recording this program from the electronics lab because this program is essentially practical. I want to give you some tips on any difficulties you might be having with the audio amplifier from Unit 9. Here's the amplifier. Now, the music you were just hearing was coming from the record player through the home kit amplifier and into this loudspeaker. And I think you'll agree it didn't sound too bad. I'll just take the pickup off the record, and then we can look at the amplifier in a bit more detail. This portion here, along the bottom part of the home kit, is where I've laid out the main amplifier. And this is designed to take an input signal at this point of about 100 millivolts from a radio tuner or a similar source and deliver 300 milliwatts to a 15 ohm load or loudspeaker. This is my loudspeaker connection. Now, the other part of the amplifier is the preamplifier, which is wired in this upper portion in what we've called the operational amplifier 1 area. And its input is coming from the magnetic pickup at this point. It's designed to take the rather weak signal of up to 5 millivolts at a kilohertz from the magnetic pickup and deliver about 100 millivolts from its output here across to the input of the main amplifier. Now, this is rather a special amplifier because its frequency response has to be shaped to compensate for the frequency response of the magnetic pickup. Now, if you remember, a magnetic pickup has a frequency response which is something like this. There's my frequency axis, there's the output, and it rises over the frequency range, something like that. Now, to compensate for that, we need a playback characteristic, in other words, the frequency response of the preamplifier, where this axis is now the voltage gain, which is the opposite of that. In other words, it falls with frequency rather like that. And this is called equalization. Well, that's why that amplifier has to be shaped like that. Now, I can't actually give you very much in the way of practical help with this amplifier during the program. It's fairly simple. If you have any problems, it's all in Home Experimental Booklet. What we ought to consider now is some of the design aspects of the main amplifier. Now, the main amplifier has to feed power, and that means substantial current, into a low impedance load, such as a loudspeaker. And I have a loudspeaker here, out of the box, of course. And you will remember that our last television program was about loudspeakers. And there we explained that current into the voice coil makes the cone either go in or out, depending on the polarity of the current. Now, it's perfectly easy to make an output stage, which, in the absence of an input signal, has an output current, a steady DC or offset current. And if that's allowed to flow through a loudspeaker, it will make the cone be displaced either inward or outward, depending on the polarity of that offset current. Now, that's not desirable because if the cone is permanently displaced, it means the loudspeaker can actually distort the reproduced sound, even though the amplifier itself is behaving perfectly linearly. So our output circuit must have no offset current, or at least very little offset current. And of course, at the same time, it's got to be able to provide a substantial signal current to drive the low impedance of the loudspeaker. And what sort of a circuit will do that? Well, over here, we have one that might be a suitable candidate. Now, you should recognize this circuit as a simple emitter-follower. We've got an NPN transistor here. Collector goes to the positive supply, and the emitter is the output point connected into the load, which is returned to 0 volts. And with 0 bias on the input, there'll be no current flowing through there. So it fulfills one requirement, no standing current. Now, what do you think will happen if we put a sine wave in, centered on 0 volts? Well, the positive signal peaks will bias the base emitter junction forward. So the transistor will come on and current will flow from the collector to the emitter into the load as required. But what do you think will happen with the negative signal peaks? Well, let's try it and see. First of all, I'll connect an oscilloscope to the output, and you can see that there's no output voltage, and in fact that trace is at 0 volts. Now let's connect the input, sine wave to the input, and now you can see that the output is in fact showing us the positive peaks coming through, but the negative ones have disappeared altogether. Now this is simply because when the signal swings negative, it reverse biases this base emitter junction and the transistor switches off. Or putting it another way, the signal can't go negative because this supply is 0 volts. So let's look at another circuit. Now this second circuit is also a simple emitter follower, and this time we're using a PNP transistor with its collector connected to -9 volts. The load, as before, goes to 0 volts, and the output comes from the emitter. And again, with 0 bias on the base, the transistor will be switched off, and so there's no standing current. We'll consider putting in a sine wave again, and let's put the oscilloscope on the output just to check that there is no standing voltage there. What do you think will happen in this case if I connect a sine wave? Well, let's do it. Well, as you might have expected, this one, because it's the dual or opposite of the other one, reproduces the negative half cycles but not the positive. And that's because when this base goes negative, it switches on this transistor, which this time is a PNP, and current flows through the load. But the positive half cycles reverse bias this junction, and the transistor switches off. So we have two circuits. Both of them produce no standing current, or very little. One of them reproduces positive peaks, and the other one negative. If only we could put these two together, perhaps we could solve the problem. Well, in this third circuit, that's exactly what we've done. This time we use two transistors. The upper one is an NPN, like in our first circuit, going to 9 volts, plus 9 volts, and the emitter is connected to the load. The lower one is a PNP, as in the second circuit, with its collector going to -9, and again its emitter goes to the load. And we drive the two bases in parallel. Let's see how well that works. I'll connect the oscilloscope to its output, and we can see that we get no output voltage in the absence of an input signal. So that bit's all right, no standing current. Now I'll put the sine wave into the input, and there you can see straight away that basically the circuit's doing what I hoped it would do. It reproduces both the positive and the negative half cycles of the input wave. But of course you can also see a terrible snag with it. It has some distortion in the region where the waveform is swinging from positive to negative and back again, in this region called the crossover region. And in fact that sort of distortion is called crossover distortion. So do we have to scrap the circuit? No, we simply incorporate it into a more complex one. In fact, this is the home kit amplifier circuit, and it uses a technique called current dumping. So how does it work? We start with a linear low-power amplifier connected via a resistor to the load. This allows a small signal current to flow directly into the load. Call it I1. The amplifier's output is also connected to the bases of the double emitter follower. And at high enough signal levels, these transistors will supply current to the load. The NPN transistor will give the positive peaks, and the PNP transistor the negative ones. Let's call this I2. Now let's look at the current in the load. That's I1 plus I2. That must be an undistorted form of the input signal. Yet we know the double emitter followers do distort. So how do we get rid of the distortion? Right, it must depend on the form of I1. If I1 looks like this, when added to I2, it will just correct the distortion. So you see the double emitter followers, or current dumpers, provide the bulk of the current, that's I2, whereas I1 just fills in to correct I2. Now the circuit has to be designed to achieve this. As things stand, at small signal levels, the current dumpers are off, but at higher levels they switch on and raise the gain of the circuit, so causing distortion. So we introduce the impedance Z2. Then, when I2 flows, it causes a voltage drop across Z2, which is fed back and brings the gain down again. But we only get linear operation when Z2 is made equal to this expression. R1 is the value of this resistor, and GOC is the mid-frequency gain of the whole amplifier. That's between this point and this. A is the gain of the low-power amplifier. A drops with frequency, falling at 6 dB per octave. So Z2 must increase with frequency. So what sort of impedance is Z2? Well, it's an inductor. The remaining components provide an input bias current for the linear amplifier and AC coupling to the input. Well, that's the theory. How about the practice? Have you wired it up, Alex?
Yes, I think that's how you want.
Oh, thanks a lot. And that's the 4 inductors, is it?
It's in the box there.
Oh, thank you. Well, I've asked Alex to wire up the circuit, just as in your home experimental booklet, except that I've got 4 inductors here, which are like the ones in the home kit, but rather different values, and we'll be coming back to that later on. I've also asked him to leave out the compensating capacitor, which should go between these terminals. And at the moment, we've no input signal. There's nothing connected to the input terminals. Well, now, if we look at the output trace on the oscilloscope, I can actually see an output in spite of the fact that there's no input signal. Let me increase the time-based speed a bit. Well, now you can see that we have an output. There's some sort of instability in the circuit. And this is because of that compensating capacitor being left out. So let me put one in and let's see if it clears it up. There we are. Now the oscilloscope is showing no output now. Now that's one form of instability that might occur simply because you've left out the capacitor. But there are 2 other capacitors I have in this circuit, here and here, which I've deliberately introduced to avoid another sort of instability that might occur. Let's look at the circuit diagram. Well, that's the circuit. Now, these 2 extra capacitors should be connected as close as possible to the collectors of the transistors, which of course are at the supply voltage. One there, and another one from the other collector here. And they come together at this point, and we'll make that a 0 volt point. So in other words, we'll bring in the 0 volt rail to there. And for best results, the load should actually be returned to that same point. And these physical connections should be as short as possible. And this is a technique which usually clears up any residual instability in the circuit, stops any oscillations occurring. So, having talked about the instability problem, just one other item I'd like to mention, that's the heat sinks on the transistors. Now, I have a separate transistor here with a heat sink, and it's difficult to explain in the text how to do this, but you can see it's easy enough when you do it. You simply press the heatsink over the transistor like that. Do it before you put the transistor in the circuit. Then you can bend the leads appropriately to fit the circuit. And when you put the transistor in, the little tab is the emitter, so that goes near the emitter connection, and that pops into the circuit. Okay, well, having sorted out some of the practical problems and got the amplifier stable and got the heat sinks on, we should be able to try it out. So let's put an input signal in. Now, I'm going to take an input signal from this instrument over here rather than the generator scope generator for a reason which I'll explain in a little while. It's a sine wave at 1 kilohertz. I'll put that into the input, and now we can look at the output. It's clearly not a sine wave. It's obviously clipping at the top and bottom. So the thing to do is to reduce the input signal if this happens. So I'll reduce that now. And now you can see we do in fact have a sine wave. We can show it a bit better, I think, if we increase the sensitivity again back to 1 volt per centimetre. All right. Now, although that looks more like a sine wave, it's still obviously got some distortion. It's got crossover distortion, rather like the double emitter follower circuit we were looking at previously. And in fact, I know what the reason for that is in this particular case, because I've deliberately put the wrong value of compensating capacitor in. That makes the gain bandwidth product of the amplifier too low, because I've put in a too big a value of capacitor. So this shows you the effect of having too large a capacitor. And if I take that one out and put in the correct value, which is 3.3 picofarads, and if you look at the if we look at the trace now, you should be able to see a small amount of crossover distortion, but it's rather difficult to see. Okay, well, it looks as though we're getting quite a linear reproduction of the input sine wave, but we can't measure anything from the oscilloscope screen. Now, if there is distortion there, it must be giving rise to harmonic products. So one way to measure it is to look at these harmonics on a spectrum analyzer. Well, I've got a spectrum analyzer here. I'm going to take its input lead to the output of the amplifier. In fact, I'll plug it across the load resistance. So now on the spectrum analyzer, we can see the spectrum of the signal that's coming out of the amplifier. This horizontal scale represents frequency, with 0 at this end, 1 kilohertz there. That's the fundamental frequency of the output from the amplifier. And if you look carefully, you can see the machine scanning across through a range of frequencies. The vertical scale is the voltage in dB. Well, so much for the scales. Let's look back at the waveform of the signal. At the moment, it's a sinusoid at the output of the amplifier. I'm going to increase the input so that the output clips like that. Now, of course, you can see lots of strong harmonics in the output at 2 kilohertz, 3, 4, and so on. And in fact, from the amplitude of these harmonics, you can calculate how much distortion there is in the output waveform. Okay, well, let's go back to the position where the amplifier isn't clipping. Now, if we look at the spectrum analyzer again, you can see that all those strong harmonics have disappeared. Now, no amplifier is perfect. There must be some distortion there, but whatever there is so low down in the noise level on the spectrum analyzer that we can't really measure the distortion. So what I'm going to do is use another instrument specially designed to measure distortion, the distortion analyzer. Now, I'm taking a sine wave out of here, as I mentioned before, into the amplifier. And that's a very pure sine wave. That's why I'm using it. You need to use a very pure sine wave if you're going to measure very small distortion products out of the amplifier. I'm going to take the output from the amplifier, which is presently going to the spectrum analyzer, away from the spectrum analyzer, and into the distortion meter instead. Now, I'll make a few adjustments to the instrument, and now I've switched this knob to the 0.1% full scale position. And if you look at the meter now, you'll see that it's reading about half scale. So the distortion we're getting is something like 0.05%. Now, that compares quite favourably with lots of amplifiers. But one of the problems with the home kit, due to the shortage of money and your time, was that we specified a cheap integrated circuit. Now, ideally, we should have had a more expensive one with a much greater gain bandwidth product so that we can apply negative feedback around it. And that way, it would have been much better specified, and therefore, the inductor value, when it's calculated, will always be correct. With the integrated circuit you have in your own home kit, it could well be slightly different in its gain bandwidth product to the design figure, and that means that the inductor is a slightly wrong value. Well, if you remember, I've got 4 inductors connected to my circuit. Here they are, and I've got them wired to a switch. So I can turn the switch and select different values of inductance. Now, if I turn to the first switch position, you can see that we're getting rather more distortion now. It's something like 0.07, 0.08% rather than the 0.05 we had before. I'll switch to another inductor value, which is higher than the design value. Well, that's very much worse. In fact, the meter's gone off scale. And the fourth one, so this is a high one too, still off scale. So let's go back to the best position again. Well, that's the harmonic distortion of the home kit amplifier. And that figure we were getting, about 0.05%, compares quite well with commercial amplifiers. But over here, we have an even better one. This is a high-quality 100-watt amplifier designed to feed into 8 ohms, and it too uses the current dumping principle. Let's test the distortion of this. To do that, I'll need to take its input lead and connect it to the output of the distortion measuring equipment, where we're getting our nice pure sine wave, and from the output of the amplifier into the distortion analyzer. Now again, I'll make a few adjustments. Now I've switched the sensitivity to 0.01% full scale. And if you look at the meter, you'll see it's reading about half scale. So the distortion we're measuring now is about 0.005%. In other words, it's about 10 times as good as the home kit amplifier, and that was pretty good. So this high-quality amplifier is doing very well indeed. Well, that's harmonic distortion. Another form of test that's mentioned in the text is overload recovery, and I thought you'd be interested in seeing that done in a few cases. What we do is take an amplifier and overload it with a sine wave. But we don't apply a continuous sine wave, we just apply a burst like this. We then look to see how well the output recovers. Well, let's see how well our good quality commercial amplifier performs. Remember, here's the input and here's the output. So the good quality amplifier recovers in negligible time. Now let's look at a much cheaper low power amplifier. Here's the input again, and here's the output. But this one still hasn't fully recovered, even after several cycles of the input waveform. Now that's primarily because the amplifier has a coupling capacitor at its output. Okay, now for the moment of truth, the home kit amplifier. Here's the input again, and here's the output. Well, that's very good. It too has recovered in negligible time. Well, in this program, I've discussed some of the aspects of the audio amplifier of Unit 9. We've looked at the design of the current dumping amplifier, how to cure instability if you get it, how well it performs as regards its distortion and its overload characteristics. I hope you have as much luck as I've had and as much fun in building and testing this amplifier.